Hello, so continuing on weekly contest 341, the last problem is minimize the total price of the trips. So what this problem says is we have an undirected, unrooted tree with n nodes, and those n nodes are numbered from 0 to n minus 1. And we get a 2D integer array edges, and those edges basically tell us that we have an edge between the nodes A and B. And each node, so the nodes, not the edges, the nodes have associated prices. And so you get that integer array where prices I is the price of the ith node, okay? And the price sum of a path is basically the sum of the prices of all the nodes on a path. So for example, if you pick this path here, the price of that path is 10 for 2 plus this 2 plus this 2, and so that will give you 14. So that's the idea. And then we have a list of trips that go from start to end, and basically means that we are doing a trip from this start node to this end node. And you could do any path you like to do this trip. And there is one condition or one thing you can do, which is you can choose some non-adjacent nodes and halve their prices. So you can't halve the price of two consecutive nodes. So for example, here you can't halve the price of 2 and 1. You have to halve the price of one of them. Okay. Similarly here, okay, you can choose either to halve the price of 0 and 3 but leave 1 because it's adjacent, or choosing to halve the price of 1 but then not halve the price of 0 and 3 because they are adjacent to it. But if you halve also the price of 1, you can't halve the price of 2 because it's adjacent. So that's the rule. And the goal is to return the minimum total price sum to do all of the trips in the list of trips. So that's the idea. Now, if we take a look at this example, the first example, we get this tree out of these edges and these prices. And the trips are from 0 to 3, 2 to 1, and 2 to 3. And so what we can do is half the price. The optimal answer is to halve the price of all of them except 1. And that will give us basically 1 is adjacent to this one, so 1 is not halved. It's adjacent to 3 and 0, so it's not halved, but they are halved, right? And then the paths to do these trips would be from 0 to 3, you could do like this. This is the best one. So, and then from 2 to 1, you do this one, and 2 to 3, you do this one. And that will give you essentially the price of 0, 1 to 3 is just 1 plus 2 plus 3, that's 6. The price of 2 to 1 is 7. And then the price of 2 to 3 is 10. And then you do the sum of all of these, and that will give you 23. Yeah, so that's the idea of the problem. Now, if we take a look here, n is not too big, right? It's up to 50. And then the prices are up to n as well, of course, because it's for each node. And the number of trips is not too big either, 100. So we should get away with trying halving all the nodes. But let's see how we can solve it. Okay, so how can we think about this? So we have a list of, we have the tree or the root, the undirected unrooted tree. And then we have the list of trips, and we have also the prices. So the trips we need to make are from 0 to 3, 2 to 1, and 2 to 3. And so what we need to do here is we can, of course, do every trip separately, but then that would be multiple passes. So maybe can we think about doing it in... Can we think about shortening that a little bit? So that's the first thing to insight here. So for these trips, the first one, we know that it's like this, okay? And so what does this actually mean for the cost? Well, the cost of each path is just the sum, right, of the path for each trip. Okay, and the path for each trip is just and then the path for each trip is just the sum, right, of the cost of each node in that path. So what does this mean? This basically, if you kind of averaged out for all the trips, for each node, the cost it contributes is just the cost of the node multiplied by many times we visited that node. So sort of a frequency of the node in the overall trips. So for example, here 2 we visited twice. So 2 we visited twice, so we have 2 multiplied by 10 because we account for it in first this path and then we account for it in this path. And then for 1 we visited twice, so it's also 2 multiplied by 1 because sorry, what's the cost of 1? It's actually 2. So 2 multiplied by 2. And then this is because we visit 1 here and we visit 1 here, we visit 1 here. So it's actually 3 because we visited in this path, in this path, and in this path. And so it needs to be 3 here. And then the cost of 3 is just we visited twice, right? So this and this multiplied by the cost, which is 6. So 2 multiplied by 6. So overall it's 20. So that's the overall cost without halving any prices. So this is solving for the generalized version if we don't halve any prices. Okay, so we can just get this and we will be able to do it then in one. Once we have the frequency, you could do it in one pass, in one DFS, right? Or not really DFS, but yeah, you could do it in one DFS and just go through everyone and by default have 0. And so if the node is not visited, you will get the cost to be 0. So that's if we don't have to halve the prices. Now, how do we do it if we have for halving the prices? Well, it's really tricky to know which one is optimal. You could think about, okay, let's pick the one with the highest frequencies, but that's not really true because then it depends on also the price. If the price is higher, then even if it occurred just once, it's better to have it, right? So, and you can't also just use the price because if the node occurred in the trips 10 times, then it's better to have 10 times and its value is just 2, it's better to halve it, right? So that's sort of the idea. There is no real good strategy. And so that leads us to trying all of them, okay? Trying all possibilities, basically trying to have every node we can, okay? And so how do we do that? What are the choices? Well, we could, for each node, we could try starting with halving that node or not halving it. Right? So basically for each node, we know that the nodes are 0 to n-1. We have 2 choices, either halve its price or not halve its price. But then if we halve its price, then there is a condition. If we halve its price, that means we can't halve its neighbor's price because you can't have adjacent nodes. And so now for the neighbors of that node, so for, let's call them, if we add them to a graph, like this, for these, you have only one choice, which is not halving them, okay? And so the only one choice, which is not half. Okay, but now since we didn't have the neighbors of that one, we can either choose to halve them or not halve them, right? Because you could choose not to have consecutive neighbors, but then you could choose to have this one and have this one, but not have these ones. And so for a node that you are allowed to have or not have, you could choose to have it or not. And so what does this tell us? Well, this tells us that the states of our recursive function that will need to do all of these choices need to have a couple of parameters. So it definitely needs the node itself. You need to know whether you are allowed to halve the node price or not, because depending on if your adjacent node was halved, you can't halve that node. And so we need to pass a can halve or not. Now the other thing, just in case there is, let's say for example, a back edge like this, we don't want to go back and revisit the node, so we just will prevent that with passing the parent here, just so that we don't go in circle. And this would be the function for our recursive function, let's call it DP, that we can call here. And that's pretty much it, right? So for each node we have these choices, either half it or not half it, and if we half it we go through the neighbor, and then we go through the neighbors, and depending on if we half it, then the neighbors can't be half it, so we pass false to this one. If we didn't half it, then we have two choices, we can either have false or true for this one, and so we pass the two for our neighbors, and then we take them in, because at the end what we are requested to return is the minimum total price for all the chips. So at the end we wanna take them in. That will be more clear once we see the code. But that's roughly the idea here. Now, how do we calculate this frequency? That's the main question here. Well, we could just use either DFS or BFS. With BFS, it should be easy because we could just create for each trip, we do the path, and then we go through the path and increment each node in that path by 1, right? And with BFS, we'll be able to get the shortest path, and so it would be optimized. Now, I think that's pretty much it. Yeah, that's pretty much it here for the solution. Now, when we have, what we will do is we will add the cost. We will add we will divide the price of the node by 2, and then multiply it by the frequency of the node, right? Because we will consider it halved. Now, if we are in the case where we are not halving it, then we'll just multiply by the price of the node, and that's pretty much it. And then when we go through the neighbors and calculate their cost, we'll just add that to the cost of the node, so that we can take the min of the cost of all the nodes. Okay, so I think that's pretty much the main idea. Once we code it up, it will be more clear. So let's code it up. Okay, so we need the first to get to have a better structure for our graph. So a node to neighbors, to a list of neighbors, and so that's what we'll do first. So we will need a default dictionary here. So we will need for each node a list. So initially your neighbors are empty, and then we'll go through the edges. And so for each graph, since this is undirected, we are going to append the destination, and then similarly like this. Actually, let's call this UV to clarify that it's undirected. So this would be U, would have V. Okay, so now that we have that graph, we need our frequency to initialize our frequency table that we will use later. So each node by default has 0 frequency, and so we initialize that like this. And then we want to go through the trips, right? And for each trip, we'll do BFS to count the frequencies of a node in the path for that trip. And so that would be something like BFS for that trip from source to destination. So we'll define our BFS function here, which will go from a source to a destination. And now what should we do with this path? Well, each node along that path should be taken into account in frequency. And so for each node in path, what we want to do is just increment the occurrences of that node, because we just found it in a path. And the frequency is basically frequency of a node. This basically is frequency of a node in all trips, okay, combined, right? Okay, so now that we have that, we need to define our BFS. So BFS, just the usual BFS. We start with a DQ, and we pass a tuple, right, of the source. And then since we want to return the path, we need to have the path here. But the path starts from the source, so we should add source here. Okay. And now we need a visited set, of course, in our BFS, so that we don't visit a node multiple times. And now we will go through our BFS. So we pop from our BFS, we will get a node. And then if we reached our destination, we should stop and just return the path. And so this actually gives us both the node and then the path. So this is our path here. And we go through the neighbors. In this is just usual BFS. We also want to record that this node was visited, and so we assign it. We add it to visited set, and then we check if the node is not visited. Then we want to visit it, which means basically we want to add it to the queue. And so what's the pair? It's going to be, the pair is basically the node and the path so far. Okay, and so the node is neighbor, and the path is just the path to get to node, which is this one, plus this new node that we just reached, so it's neighbor, like this. And that should be pretty much it. We can exit like this. We are guaranteed that the node is there, so we should end up reaching this. So we actually don't need to return anything here, but if you have to, you can return an empty list. Okay, so now this should work. We could just first print frequency map just to make sure this is working correctly, and looks like it's good. Since we traverse 0 just 1 3 times, 3 2 times, and 2 2 times. Okay, so now we need to do the other function that will actually try halving the nodes or not, halving the prices of a node or not. So we said that the state of that function is going to be the node, its parent, and whether we can halve it or not. Okay. And so what we need here then is we check if we can halve the node. Then the cost of that is going to be the frequency of the node multiplied by the price of the node divided by 2. Okay, so if we can halve it, it's the frequency of the node multiplied by the price halved. If we can't halve it, then it's going to be just the cost. So this what this node contributes. Okay, and now we are going to go visit the neighbors of this node. Okay, and so to do that, we will just go through the neighbors of the graph, the neighbors of the node in the graph, and we want to check if the node can be halved. If the node can be halved, then the cost of that node contributes is we visit the neighbor, the parent is just the node. Now, can we pass half, false, or true here? Well, the node that is adjacent to this neighbor was halved, right? Because we can halve it. And so this actually just should have, just to make sure. So this means basically we halved the node with the price of the node. So we can't halve the price of its adjacent neighbor. And so we have to put false here. Now, otherwise, we have two choices. We can either, because we are allowed to halve, and so we could either decide to halve it or not. And so we try both and take the minimum. And so we try not halving it, and then we try halving it. So half that would be true here. And then we want to add that to the total cost for this node, because this is the cost of the node of the node's subtree. Okay, and so this would need to be, because at the end we'll get the total cost, and so this plus the neighbor cost, the optimal neighbor cost. And then at the end we want to return the cost, the overall cost for this node and its children. And now what should we do to call it here? Well, we don't know halving which node first will give us the right answer, and so we want to try all of them. And so all of the nodes are just from 0 to n-1. Okay, and what we want to do here is do dp of the node. The parent initially is just none. Okay, but we want to try both, starting with this node and halving its price, and not starting with halving its price, because we don't know which one is optimal, and so we try both again, similar to what we did here. Okay, and so we try both true here, and we take the min, and this would be the cost, and we will just define the cost initially as the largest number possible, so that we always get an answer from this. And so we do infinity, and then we return that cost. Now, there is just one other thing we need to do here. Remember, we pass it parent so that we don't go back to it. And so we need to check that this neighbor is actually not the parent, so that we don't go back. And we can move this over here, and run it. Okay, looks accepted. If we submit, we'll probably get time limit exceeded because this function can get called multiple times with the same parameters, and so we will need to memorize it, right? So you can see here we got time limit exceeded, and so to handle that we will need to cache this this DP function. And so let's create a memo table to cache it. So that would be just hash map like this. And then what we will need to do is in our DP function here, just check if node parent and should have, right? So all of these conditions are in memo. This means the function was called before, so we want to just use the result from before. And so we could just use this pair as this tuple as the key, and so we return it. Now if it wasn't calculated before, then we want to save it for next time. Okay, so let's run this. Looks good. Let's submit. Okay, it looks like we have a small problem with this here. Okay, so we actually have a problem here because we didn't minimize with the cost so far each time, and so we need to do that. Yeah, sorry, there is a typo here. I'm surprised that this didn't get caught. So with this, we need, in more test cases, this would need to be, right, we are going through the nodes from 0 to n minus, and now if we run this, it passes. Okay, yeah, so that's pretty much it for this problem. Yeah, pretty cool problem actually. Please like and subscribe, and see you on the next one. Bye.